video we're going to be looking at polarity of molecules. Polarity is looking at the charge distribution in a molecule. Before we can start though, we need to revise what electronegativity is. So electronegativity is the ability of an atom to attract an electron within a covalent bond. So there is a general trend. As you go across the periodic table, the electronegativity increases. This is because you've increased the number of protons in the nucleus, which means you've increased the effective nuclear charge. This gives it a stronger ability to attract the electrons within a bond. As you go up the periodic table, electronegativity also increases. That's because they are smaller atoms, and smaller atoms are better able to attract the electrons within a bond. Remember, electronegativity is about a tug of war for electrons. A non-polar bond occurs when you have two atoms that are exactly the same, like two chlorines or two hydrogens. This means the difference in electronegativity is equal to 0. It's the equivalent of having two twins tug of war on some electrons. So think of two twins, they're exactly the same. They're tug-of-warring on those electrons, exactly the same. So there's no uneven charge distribution. Now, a polar covalent bond occurs when there's a difference in the electronegativity, and it's less than 2. So what you have here is you have one which is much bigger. My drawings of an elephant are not very good. And one which is much smaller, which is not happening in my picture. This creates a difference in electronegativity of less than 2 and results in a polar covalent bond. Now, an ionic bond occurs when the difference in electronegativity is greater than 2. You get a complete transfer of electrons. So this is like having a huge elephant with something so small that it cannot hang on and it wins. So this one has completely won the tug of war. So to give you a general overview, to work out if a molecule is polar or non-polar, the first thing I want you to look at is the shape. There are symmetrical shapes and there are non-symmetrical shapes. Non-symmetrical shapes are things like pyramidal and bent. These are automatically polar because they're unsymmetrical. Symmetrical shapes such as linear, triangular planar, tetrahedral can be either polar or non-polar. To work it out, we need to look at what the bond dipoles are doing. If the bond dipoles sum to 0, then it's a non-polar molecule. If the bond dipoles don't sum to 0, then it's a polar molecule. And if it's a polar molecule, this means it has an unequal charge distribution. So let's look at some non-symmetrical shapes first. The first example we're looking at is ammonia. Now remember, ammonia looks like this. It's a pyramidal molecule. Now what happens here is that the nitrogen is more electronegative than the hydrogen, so it's pulling the electrons in towards it. So this one here has a positive dipole, and this equivalently has 3 negative dipoles. So the sum of the dipole is towards the nitrogen. So this is a polar molecule. So once again, so we have positive, 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 3 lots of negative. The overall charge is this one. Another non-symmetrical shape is water. Water looks like this. Now what's happening here is the oxygen is more electronegative than the hydrogen, so it pulls them in this way. The overall giving a 2 net dipoles, and the overall charge is towards this direction, which you can see here. This gives a net dipole, so it is a polar molecule because it has an uneven charge distribution. Now let's look at some symmetrically shaped molecules. The first shape we're going to look at is linear. So linear can either be polar molecule or a non-polar molecule, depending on how the sum of the dipoles works. Our first example is hydrogen. Because the sum of the difference in electronegativity here is equal to 0, hydrogen is a non-polar molecule because it has an equal charge distribution. So here the sum of the dipoles is equal to 0. With HCl, however, it's slightly different. Now chlorine has an electronegativity of 3.2, hydrogen has an electronegativity of 2.2, so the difference in electronegativity is 1, which means it's a polar covalent bond. Now what you've got here is chlorine is more electronegative than hydrogen, so that means the electrons are being pulled towards chlorine, giving it a negative dipole, and the hydrogen a positive dipole. So the sum of the dipoles is not equal to 0 here. It has an uneven charge distribution. So it is a polar molecule. This one here is an example of carbon dioxide. Carbon has an electronegativity of 2.6 and oxygen has an electronegativity of 3.4. So the carbon-oxygen bond is polar covalent with a difference in electronegativity of 0.8. Now, because what we have here is we have carbon bonded to oxygen, which is bonded to oxygen. The difference in electronegativity means that the oxygen is pulling out this way and the oxygen is pulling out this way. The sum of these vectors is going to be the same, so the sum of the dipoles is equal to 0. This means it's a non-polar molecule and it has an even charge distribution. This time I'm going to look at an example of triangular planar. Triangular planar is once again a symmetrical shape. Let's look at the actual example we've got here, which is sulfur trioxide. In this, the sulfur oxygen bond is a polar covalent bond. Sulfur's electronegativity is 2.6, oxygen is 3.4, which means each of these bonds is polar with an electronegativity difference of 0.8. So it's going to pull out towards the oxygen in each case. Now, what this will result in is if you sum these vectorially, the sum of the dipoles will equal 0. So this will result in a non-polar molecule with an even charge distribution. Now, if we change this from sulfur trioxide to something else like SO2Cl, because here you will have a situation which looks like this, and you will have the oxygens pulling out to the sulfur from the sulfur and the chlorine pulling out from the sulfur. However, this electronegativity difference is 0.8. This one here is 0.8, but the sulfur chlorine bond is in fact 0.6. So here you can see the sum of the dipoles will not equal 0. So this here would be a polar molecule. Tetrahedral is another example of a symmetrical shape. In this particular example, we have methane. So here we have hydrogen, 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 and hydrogen. The carbon-hydrogen bond is polar covalent. Carbon's electronegativity is 2.6, hydrogen's is 2.2. So in this case, it is being pulled in towards the carbon. These will sum vectorially, and the sum of the dipoles in this case will equal 0, so there is no net dipole. So therefore it is a non-polar molecule, which means it's got an even charge distribution. This here is a different example. This one here is CH3Cl. In this particular case, you can see you've got carbon, chlorine, hydrogen, and hydrogen. So the carbon-hydrogen bond is polar covalent, and remember, in this case, it pulls in. So this is a positive dipole, negative, positive, positive, and negative. So you've got 3 negatives pulling in. Each one has a polar covalent bond of 0.4. In this particular case here though, the chlorine is more electronegative than the carbon. So chlorine is 3.2, carbon is 2.6, so it's going to pull out here to 0.6, so this will be negative to this one's positive. So here, because you've got one pulling in, one pulling in, one pulling in, and then a bigger one pulling out, the sum of the dipoles does not equal 0, so therefore it is a polar molecule. Now I've chosen to show you this example because it's a little bit confusing if you just draw it on paper. This one drawn on two-dimensional paper could be drawn looking almost non-polar, but it isn't, because when you draw it three-dimensionally, what happens is that you have a chlorine, and a hydrogen. So looking at the electronegativities, this one pulls in, this one pulls in, this one pulls out, this one pulls out. So we show the dipoles. what you would have vectorially is you will have pulling in like this, then you'll have a much bigger pull outwards. So the sum of the dipoles goes through here and is not equal to 0. So therefore it is a polar molecule with an uneven charge distribution. I need you to try some yourself, so go to the OneNote, look at shape and polarity, and do some examples.